All right, so here's section 2.2. This is on characteristics of functions. So we're going to be taking a look at different characteristics of functions here. There's going to be about four sections, and this is another 4-page of notes. Oh, I just added a page on accident. Okay, so let's start with looking at x and y intercepts. So this should be some review for you here. Let's look at, I already filled some of these blanks in. Intercepts are points where a graph intersects the x or y axis. Okay, so that's where we're crossing one of the axes. An x-intercept occurs when y equals 0. Okay, so I do have some students that get kind of confused which intercept is happening at which axis. So let's look at this. An x-intercept, like right here, is where it crosses the y-axis. Okay, so this is where y is equal to 0. Okay, and y-intercept is just the opposite. It occurs where x equals 0. So we're crossing the x-axis, and that can be shown right here. Okay, so this is also really important as part of your definition of a function. A function can have 0 plus x-intercepts, but at most one y-intercept. Okay, so if we just take a second to think about this for a minute, 0 plus means it can have 0 x-intercepts. It might not ever cross the y-axis, right? So you could have a function that was like this, you know, a parabola that goes up. It doesn't ever cross the x-axis. I'm sorry, it doesn't ever cross the x-axis. So, or the y, hang on. It doesn't ever cross the x-axis, so there are no x-intercepts, okay? But it can also have more than one, like this one, this function over here is a parabola. We cross the x-axis at 2 different spots. There we have 2 different intercepts, okay? But when we talk about y-intercepts, it can only have one y-intercept, and that's because our functions, right, if we have for our y-intercept, we have a value of x equals 0. And x equals 0, for every x value, we can only have one y value. So that means we can only have one y-intercept. When x equals 0, there's only one y value, only one spot where it crosses. Okay, so that's part of the definition of a function there. So let's look at some examples. Our directions here are to identify the x and y intercepts of the functions graphed below. Okay, so first of all, I'll just let you know that when you're asked for an x-intercept, you're always going to give it in a coordinate, as a coordinate pair. Okay, and because at your x-intercepts, your y is always 0, so you're just going to have a coordinate pair where you have the x value, comma, 0. Y is always going to be 0. Okay, and this x value here is the value of x where it crosses the x-axis. Okay, so let's take a look at the graph here. So again, we're looking at the x-axis here, which is this axis, and we're looking for points where the graph crosses it. Okay, so it looks like we have one point here. So if we were to find this coordinate pair, our x value would be 1, 2, 3, 4. And of course our y value would be 0, which we already know, but you can see that because everything on the x-axis, y is equal to 0. Okay, there's only one x-intercept in this graph. So let's look at the y-intercept. So the y-intercept is a coordinate point where x is equal to 0. So we can already fill in 0 for the x because it's always going to be 0 for y-intercepts. And then we look along the y-axis for a place where the graph crosses. Okay, and again, this can only be in one spot. And you can see that also because of our vertical line test, for a relation to be a function, if you draw a vertical line and say this is the specific vertical line on the y-axis, it can only cross the function one time, and so that's another way we determine whether a relation is a function. Okay, so looking at the y-axis, we're looking for a spot where the the graph crosses. And in this case, it doesn't actually cross, it stops right on the axis, but that counts as well. So it looks like our y is positive 2 here. So our y-intercept is 0, 2. We'll only have one x-intercept and definitely only have one y-intercept. All right, so let's move on to number 2. X-intercept. So I see us crossing the x-axis at 1, 2, 3, 4 spots. Okay, so we're going to have 4 x-intercepts. And for each of those x-intercepts, we're going to write them as a coordinate pair, and the y value will be 0 for all of them. So let's look at the first one here. It looks like our x is -1, so we have -1, 0. This next one here, it looks like our x is +1, so we have +1, 0. This one, x is +2, 0. And then this last one, x is equal to 3 and y is equal to 0. All right, so we should only have one y-intercept here. So looking along the y-axis, it only crosses at one spot. Looks like that's 1, 2, 3, 4, 5, 6. Okay, so the x value will always be 0, and the y value will be 6 in this case. Looking at number 3, x-intercepts, it looks like we have 1, 2 here. This first one is 1, 2, 3, 4, -4. Y is equal to 0. And then the other one, x is equal to 2, y is equal to 0. And then our y-intercept, it only crosses in one spot, and that's right here at -2. So our x is 0, our y is -2. All right, number 4, looking at x-intercepts here. So our parabola opens up, and it starts above the x-axis, so it never crosses the x-axis. So we don't have any x-intercepts, okay? But we do have a y-intercept. It looks like it crosses right here. So we have 1, 2, 3, 4, 5. Our x value, of course, is 0. Our y value is 5. All right, and number 5 here, it crosses the x-axis in 2 different spots. So the first one, it looks like 1, 2, 3, y is 0. And the other one, 3, 4, 5, 6, 7, and y is 0. Our y-intercept is down here. We only have one of them, 1, 2, 3, 4, 5, 6. So our x is 0, of course, and our y is -6. And then we are looking at number 6 here. 6 is an interesting one because it looks like we have 2 asymptotes. So we kind of talked about asymptotes a little bit in the last section here. So asymptotes, as a reminder, these are like invisible lines, or they're not part of the actual function's graph, but they are lines where the graph approaches but never touches or crosses. Okay? So we have these asymptotes here on the x and y axis where x is equal to 0 and y is equal to 0. So that means we're never crossing the x-axis here. So x-intercepts, we have none. And then our our asymptote of x equals 0 is a vertical line on the y-axis. That means that our function is never going to touch or cross 0. So we will never have a y value when x is 0, and so we therefore do not have any y-intercepts either. Okay, so there's our first look at x and y intercepts. So let's take a look at zeros. Okay, and zeros are they're very, very, very similar to, well, they're exactly the same as x-intercepts. Okay, so this is where we're crossing the x-axis. Okay, so zeros, we can also, they're related to, please stop moving. They're related to x-intercepts. You might have also heard them called roots. Roots, solutions. I think there's another one. It might come to me. If it comes to me, I'll write it down. But these are pretty much interchangeable: zeros, roots, solutions, that kind of thing. So these are the values of x when y is equal to 0. Okay, so the definition that I have written down here is the points at which the function intersects the x-axis. Okay, Using function notation to find zeros, so this is to find intercepts algebraically, okay, which is a little bit different here. So this is not using a graph. We're going to just use the equation for the function and then find our intercepts that way. So to find zeros, set f of x equal to 0 and solve for x. Okay, so we're going to set the entire function equal to 0 and then solve for x. And then to find the y-intercept, you find f of 0. So if you're still a little bit confused on function notation, you need to work with a little bit more, because this is saying y equals 0, right? That's where x-intercepts happen, where y equals 0. And this is saying x is equal to 0, okay? So we're saying the same thing that we did initially. Now we're just using function notation. Okay, so let's look at these algebraically here. So number 7, we have find the zeros and y-intercept of each function algebraically. So to find zeros, again, we set f of x equal to 0. Okay, so that means f of x is equal to negative absolute value of x minus 5 plus 3. We set this whole thing equal to 0. Okay, so this is just, now what we have is we're just solving this absolute value equation here, and we all know how to do that from last section. So we will divide both sides. Well, let's see, let's subtract 3 first. Then we have the negative absolute value of x minus 5 is equal to negative 3, divided by negative 1 on both sides. We have the absolute value of x minus 5 is equal to 3. Then we split these up into two conditions. We have x minus 5 is equal to 3. X minus 5 is equal to negative 3. We'll add 5 to both sides here to solve. On this side, and this one we get x is equal to 8, and this one we get x is equal to 2. Okay, so our zeros here are x is equal to 8 and x is equal to 2. So here we'll write this in our set notation. X is equal to, the smaller one is 2, larger one is 8. Okay, and then finding the y-intercept, we find what f of 0 is equal to. So this one is much easier. We just enter in 0 everywhere we have x. Okay, so our function is negative absolute value of x minus 5 plus 3 is equal to 0. So we'll just pop a 0 in for x minus 5 plus 3. We get negative, the absolute value of negative 5 plus 3. Then we get negative 5 plus 3. And then we get negative 2. So our y-intercept is, you know, when we're giving intercepts, our notation's always going to be an ordered pair, so 0, negative 2. But here, since they were asking for zeros and not the x-intercept, we just give the values of x when y is equal to 0, or the values of x where it crosses the x-axis, okay? So when we're asked to give values, we can just list them. If there's more than one, we can just list them in set notation. But if we are giving it intercept, it needs to be a coordinate point, okay? So there's a little bit of notation there. All right, number 8. So same thing, we'll set this entire thing equal to 0 to find the zeros. And it looks like we have a quadratic here. So I'm going to look at factoring first. It looks like there's no GCF. If I do the slip and slide, I'll have negative 8 adding up to negative 7. So it looks like that can work. We'll have, I'll just take this, multiply it by the n, x squared minus 7x minus 8. Then we can factor this. Of course, this still equals 0, still equals 0. We'll factor this as x minus 8, x plus 1. And then don't forget to divide by 2. We're going to get x minus 4 and 2x plus 1 is equal to 0. So here, if we set each of these equal to 0, x minus 4 is equal to 0, x is equal to 4. And then 2x plus 1 is equal to 0, x is equal to negative 1/2. Our zeros are x is equal to negative 1 over 2 and positive 4. All right, and then looking for the y-intercept, let's label these zeros, y-intercept. Then we just find f of 0. So we have 2 times 0 squared minus 7 times 0 minus 4. This one's really easy because this becomes 0 and this becomes 0. We're just left with negative 4. So our coordinate pair is always going to be 0 first, and then our y value, which is negative 4. I was gonna just label these zeros and y-intercept. Okay, so let's take a look at number 9. So here we're going to set this whole thing equal to 0. It looks like we don't have a quadratic, but we have something here that we can factor. Okay, it is an even root, so it can be treated similar to a quadratic. So let's just go ahead and factor this right off the bat. We have x squared. Let's do negative 4 and negative 1. That will equal negative 5 and positive 4. So then it looks like we can factor both of these look like difference of squares. So let's factor x squared minus 4. We have x minus 2, x plus 2. And then we'll have x minus 1, x plus 1 is equal to 0. This is fully factored now. We can set each of these equal to 0 and solve. So we can set each of these individually to 0 and solve, but I know that these two are going to give me positive and negative 2 as my answers, as my solutions, and then these two are going to give me positive and negative 1. So I'm just going to write that a little more compact here. Okay, so we have 4 zeros here, which we knew because the degree is 4. So our zeros, I'm just going to write as x is equal to plus or minus 1 and plus or minus 2. I know when you list the plus or minuses, it's a little hard to determine which one's going to go first, but really that's not as important here. Okay, so finding the y-intercept, we just find f of 0. So we have 0 to the 4th minus 5 times 0 squared plus 4. Again, this is going to be 0, this is going to be 0, and we're going to be left with 4. So our y-intercept is 0, 4. Looking at number 10, let's set this equal to 0 and solve. I am going to factor this. It looks like we have a greatest common factor of x here. So if I factor an x out, I'm left with x squared minus 6x minus 7. That is equal to 0. And then I can factor this quadratic here. So I'll keep the x out front. Factoring the quadratic, I should have x and x. Let's do minus 7 and plus 1. And then we set each of these factors equal to 0. So this is a factor, don't forget. So x equals 0 here, x minus 7 equals 0, and x plus 1 equals 0. This one's already solved. This one we're just going to add 7. This one we're going to subtract 1. So we have 3 solutions here, which we knew because the degree is 3. So listing out our zeros, we have x is equal to negative 1, 0, and 7. Finding our y-intercept, we're just going to find f of 0. And this one looks like it's going to be super easy again because each of these are being multiplied by x, and if x is equal to 0, they all will equal 0. So here, our y-intercept, x of course is 0, y is 0 here, so it looks like this function crosses through the origin. All right, number 11. So let's solve this one. Set it equal to 0. Solve it. It looks like I have a GCF here of just x, so we'll factor this x out. We'll be left with 3x squared plus 13x minus 10. That's equal to 0. If I do the slip and slide, I'll have 30 and 13. I have 15 and 2. Okay, so let's factor this using the slip and slide method here. We'll keep this x out front. X squared plus 13x minus 30. That's equal to 0. And then we'll factor this out. I know I have a 15 and a 2, and I want a positive 15 and a minus 2 to get 13. Then let's not forget we're dividing by our a again. So we have x times x plus 5 times 3x minus 2 equals 0. So each of our factors equal to 0. So x equals 0, x plus 5 equals 0, and 3x minus 2 equals 0. This one's solved. This one, x is going to equal negative 5. And this is supposed to be a 2. And then we should have x is equal to 2/3, I believe. Okay, our 3 solutions here, which we knew we were going to have because of the degree of 3. So our zeros are x is equal to, smallest is negative 5, then we have 0, then we have 2/3. Okay, for our y-intercept, we're just finding f of 0. So we have 3 times 0 cubed plus 13 times 0 squared minus 10 times 0. This will all give us just 0. So our intercept again is 0, 0. This one also goes to the origin. Number 12, last one here. Okay, so we'll set this equal to 0. We know how to solve radical solutions. First, we want to add 2 to both sides. So we'll have x plus 1 is equal to 2. Then we're going to square both sides. We get x plus 1 is equal to plus or minus 4. No, that's the square root. We don't need to. X plus 1 is just equal to 4. Sorry. And then we'll subtract 1. X is equal to 3. Our 0 is, we just have one value here, x is equal to 3. And then for our y-intercept, we're finding f of 0. That means we have the square root of 0 plus 1. And then on the outside, minus 2. The 0 plus 1 is equal to 1, minus 2. The square root of 1 is equal to 1. We're just going to be working with principal roots here. And then 1 minus 2 is negative 1. So our y-intercept is going to be, x is going to be 0, of course, and negative 1. Okay. All right, that's it for finding intercepts algebraically. Let's take a look at critical points here. So critical points are points where the graph changes its direction or shape. Okay, so we have critical points where the graph changes its direction or shape. Okay, so let's look at what these are called specifically. So if it changes direction, that's called an extrema. Okay, so that's where we are going. In this case, we're going up, 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 and then now we're going down, down, down. Okay, so this maximum, this extrema, is where we're changing direction, and that's considered a critical point. The other type of extrema is when we're changing direction, like here we're going down, and then we change to go up. That is also a critical point. It's also an extrema, and we call that a minimum. And the last one here is a point of inflection. That's where the graph changes its shape. So here we're not changing direction, we're going down, 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 but we are, instead of having this this part where it kind of looks like we're curving up, now we're curving down. Okay, so at this point we changed from curving up to curving down. Okay, and this is the critical point. It's called a point of inflection. All right, so let's talk about relative and absolute extrema. So we talked about the two different types of extrema in general, which is a maximum and a minimum. But we have two types of each kind. Okay, so a point where the greatest value, a point with the greatest value compared to points around it is a relative maximum. Okay, and then let's look at an absolute maximum first, and then we'll look at what they look like on the graph. So the point with the greatest value over the entire domain of the function is going to be an absolute maximum. Okay, so the difference between a relative and an absolute maximum, let's look over here, okay? So a relative maximum, this says it's the greatest value compared to points around it, okay? So if we look at this point here, we're just looking at the points surrounding it. This is the greatest value compared to the graph that's on either side of it, okay? And then this is also a relative maximum here, right? This is the greatest point compared to points around it. But since this relative maximum is greater than this relative maximum, we also call this the absolute maximum because there are no points higher. So this is the top point of the range here. It's the highest y value that this function is going to have. Okay, so relative and absolute maximum. Let's look at the minimum. So we have a relative minimum where we have a point with the least value compared to the points around it. Okay, so these are both relative minimums right here. You can see that all the points on either side of it are greater than these points. So they are minimums and they're called relative minimums. And then we have an absolute minimum. And that's the point with the least value over the entire domain of the function. So the very, very low end of the function is going to be the absolute. So between these two relative minima, this one will be considered the absolute minimum because it's lower than the other one. Okay, so let's look at some examples. So the directions here are to give the coordinates and classify the extrema for the graph of each function. So again, when we talk about extrema, we're talking about points where the graph changes direction. It's a maximum or a minimum. And does it give the function here? Okay, so give the coordinates, classify the extrema. So we're looking for different types of extrema, and then we're going to decide whether they're absolute or relative, and whether they're minima or maxima. And use your graphing calculator to approximate if needed. So let's look at number one here. So we're looking for minimums or maximums. Okay, it looks like we only have one here, and it's at this point here. It's a minimum. And it's also going to be considered the absolute minimum because it's the lowest point in the range here. So this point, it looks like it's x value 1, 2, 3, 4. So the point is 4, 1, 2, 3, 4, 5, negative 5. And we're going to call this an absolute minimum. Okay, number two, it looks like we have a couple different things going on here. We have a maximum here, a minimum here, and a maximum here. Okay, so let's look at the maximums here. So between this one and this one, we're going to label this top one the absolute maximum. Okay, so we have the absolute maximum. We need to give the coordinate for that. These don't look like they're on exact points, and I haven't taught you guys how to use your graphing calculator. So let's just approximate just without a graphing calculator. Okay, so we have negative 1. This looks like it's between negative 1 and negative 2, so let's say negative 1.5, and then 1, 2, 3, positive 3. Okay, looking at our other maximum, we're going to call this a relative maximum. All right, and we're looking at this guy right here. It's kind of hard to see exactly what's going on. Let's zoom in a little bit. So we want this point here. Oops. We want this point here. So let's say x value is 1. It looks like it's about a third of the way through, so we'll say 1.3, and the y value 1, 2, let's say 2.6. Okay, so I'm just approximating here. And then we do have this other extrema here, which is our a minimum. So we'll just call this a relative minimum. And we'll say that this is at 0.3. It looks like it's about a third of the way between 0 and 1, and then 1, 2, 3, 4. We'll just go with 4.2 here. Okay, so I'm just guessing here. Anything close-ish will be fine when you're doing these. Okay, so I do also want to point out that we have this minimum here, and it's the only minimum that we can kind of put our finger on here, but we do not count it as the absolute minimum because the function is still decreasing, and it's going to the y values are still getting smaller as these arrows point down, and we're never going to be able to put our finger on the absolute minimum because it goes in the negative direction forever. Okay, so there will be some cases where we'll have minimums and maximums we have relative minimums and maximums, but no absolute minimum or maximum. Okay, so that's number one and number two. Two more examples here, and then we get into increasing and decreasing. Okay, so we're looking for extrema again. That means minimums and maximums. Okay, and here's another case where this function is going in the positive y direction forever and in the negative y direction forever. Okay, so we're not going to have an absolute minimum or maximum in this case. But since it does change directions in two places, we will have relatives. Relative maximum and maximum minima here. Okay, so let's look at this one first, this relative minimum. I'm just going to start abbreviating here. It looks like this is at 1, 2, 3, negative 3, and 1, 2, 3, 4, 5, and negative 5. Easy peasy. Okay, and then we do have this relative maximum here, and this one's not on the grid exactly, but we'll say that's negative. Well, first let's relative max. I'm going to say that this is at negative 0.3 and 1, 2, 3, 4.5. Okay, and the last one here. Oh, we have a point of inflection. Okay, so no absolute minimum or maximum here because we're going in the negative and positive direction forever. Okay, but it looks like we do have a relative minimum, a relative maximum, and a point of inflection, which is considered a critical point. Okay, so let's look at the relative maximum first. That is... It looks like negative 1.4 and 1, 2, 3, 4, 5, 6. Okay, and then our relative min would be, I'm going to say at 1.4 and 0 here. And then our point of inflection, so we're going down and we're still going down, so we didn't change direction, but our shape changed. We were I forget which one's concave and convex, but we changed from one to the other here. Okay, and these points they get pretty important when we are taking calculus. So for those of you who are moving on next year, it's good to remember this inflection. And it looks like that is at x is equal to 0, y is equal to 3 here. All right, so there are our critical points. Let's look at increasing and decreasing behavior. Okay, so moving from left to right, a function may increase, decrease, let's do different highlights, decrease, or remain constant on certain intervals. Okay, so I want to point out right now that the interval is always going to be the part of the domain that this behavior is happening. So we're always talking about the x values over which these things are occurring. Okay, so if we look, we are increasing here. Okay, so since we have this arrow over here, it means this we're doing this forever. It's going in the same pattern forever in the negative direction, okay? So the x value that this starts at, well, it never really starts anywhere, but we represent that with negative infinity. Okay, and this is an interval, right? So we're going to use interval notation, and this comes all the way up to -1, and we're never going to use brackets here because at these specific points we can't say whether they're increasing or decreasing, because that's when we change directions. Okay, and then we are constant on this interval from here to here, where we're not going up and we're not going down. We're just staying straight across at the same y value. Okay, and that is from -1. It looks like 1, 2, 3, 4 to 4. All right, and then lastly, we're going to be decreasing here where our y values are going down on this interval. And it looks like that starts at 4, and it's going to go on to infinity. Okay, so these are the intervals of the domain, the x values over which these are happening. Okay, so let's look at these examples. It looks like there's 6 here. So increasing intervals, we are increasing from here to here. Okay, so let's write that. It looks like that's 1, 2, 3. So it starts at x is equal to 3, and it goes on forever because of the arrow there. And then if we look at decreasing, it looks like it starts over here and comes down to this point. Okay, because of that arrow, we're decreasing forever. We're decreasing forever in the negative, starting at negative infinity, and we're going to decrease all the way to 3 and stop. All right, number 6, increasing intervals. So it doesn't look like, so it looks like here we're going down, down, down. We're still going down here, although the slope is a little bit smaller. And then here we're going down with a steeper slope. Okay, so we are not increasing on any intervals here, but we are decreasing everywhere else except, get my red out here, it looks like we have another asymptote on this line. So our function's never going to cross this line, and it's never going to be defined at this line, so we can't say that it's decreasing or increasing or remaining constant at this x value because it is not defined at this x value. This x value is not included in the domain. Okay, but we can say we're going from negative infinity all the way up to 1, 2, 3, 4, -5. And then, starting at -5 all the way to positive infinity, we're also decreasing. So we're decreasing on both of these sections here. We just can't include -5 because it's not included in the domain. Okay, looking at number 7, it looks like we are just increasing this whole time. Okay, our y values from left to right are just going to get bigger. So that is from negative infinity all the way to infinity. And then our decreasing intervals, we have none of those. Number 8 here. Okay, so it looks like we change up quite a bit here. So we're decreasing here, we're increasing here, and we're decreasing here. Okay, so looking at our increasing intervals, it looks like it's only 1, and that's from this point to this point. So let's say from x is equal to 0, again these are x values that we're looking at, all the way to 1, 2.5, just guesstimating here, and that's it. But we are decreasing over 2 intervals. We'll start at negative infinity and we'll come all the way up to 0. That's when we start increasing. And then when we hit 2.5, that's when we change directions and start decreasing again. And that goes all the way to infinity. Number 9, increasing intervals. We just have this one here from here to here. So we are increasing from, and we have this one here. And we're increasing from here all the way up. Okay, so we have, let's see, it's kind of hard to see these graphs. -1, 2, we'll say -1.9, all the way up to 0, and then again from 1.1 to infinity. And again, I'm just guesstimating on these x values here. Decreasing intervals, we start at negative infinity, and we're going all the way to negative 1.9, where it starts increasing. And then again, from 0 to 1.1. Okay. Let's look at the last one here. So increasing intervals, we're increasing here. Looks like we're decreasing here and increasing here. So we start at negative infinity. We'll come all the way up to negative 1.1. And then starting at 1.1 again, we go to infinity. And decreasing just on this one interval, so it's going to be negative 1.1 all the way to positive 1.1. That's the only interval where this one is decreasing. And that is our section 2.1 notes. I think I just repeated this page on accident.